Yeah, my name's Jonathan Ross. I'm here to discuss obfuscation in PDF malware and how I nearly created a FUD. So, about myself, I'm a fourth year ethical hacking student here at Abertay, who's coincidentally enough looking for a grad job. I'm currently interning as a cybersecurity consultant with Curious Frank, which is a division of the Scottish Business Resilience Centre. I've got past experience in IT support. My interests include red teaming and offensive security, anti-phishing, and what was the other one I said? Human-based security. So yeah, a bit about what's to come. I'm going to start covering about the basics of PDFs themselves and malware, some of the obfuscation techniques, how they work, how these obfuscation techniques can be applied, and evaluating them, how effective they are or not at evading antivirus, and then going to open the floor up to questions. Before I start, though, I'd like to give a big shout out to Didier Stevens, because I base a lot of my work off his. He's kind of like the grandfather of the kind of PDF malware and document-based malware. So, here for dummies, back to basics. So, for those who don't know, basically what a PDF is a document, obviously, but it's kind of praised due to its rich feature set and compatibility, the idea of cross-platform. So, it's very widely available. So, it's kind of interesting because PDFs can contain embedded executables, or even be used to execute JavaScript embedded within it. So the JavaScript is kind of used for more like sort of enhancing appearance in addition to like kind of dynamic forms and tables. So in terms of the actual structure of a PDF, it's consisted of 4 parts. You've got the header, which is the kind of tells you the version of the PDF that's been used. The body, which is made up of objects. So this is where all your content is, all your images, all your forms and stuff like that. The cross-reference table, or the XREF table, so that specifies the positioning of all these objects. And then there's a trailer, which has information about where the document starts. So, in terms of actual objects, within the body, they can include the likes of numbers, arrays, dictionaries, or streams. So streams are really important. So that's, I'm going to discuss that more later, but that's more about, in streams, that's where you can physically embed data. So this is an example. Let's take one of semantics papers on PDF malware. At the top here, we've got the PDF header, and then a first object declaration, second one here, and then we've got the cross-reference table and the trailer. So moving on to PDF malware, like itself. So why is it being used? So it's kind of, if you think about it, it's less well known than macro-based malware, at least in my opinion. When I was doing this project for university, the first thing I did was I Googled PDF malware. And believe it or not, the first thing that came up in Google was, can a PDF contain malware? Which I thought was quite interesting. But to kind of put it into context, Symantec in the 2010 paper, The Rise of PDF Malware, actually said that the PDF malware is up, macro malware is down, kind of the pattern. And also, a bit more context. So everyone's like, yeah, you can execute the malware, but are there vulnerabilities? In Patch Tuesday on December of last year, Adobe actually fixed 87 vulnerabilities within Reader. So there are vulnerabilities out there. And also virtually every PC has a PDF reader. So the attack surface is a lot wider than someone, for example, using Microsoft Office. In terms of actually executing the malware, it can be done with either within JavaScript, within PDF streams, as I discussed, or it can be executed via executables that's triggered on opening the PDF. Now, currently, the JavaScript-based kind of malware is more popular purely because back in 2010, in Adobe Reader 9, version 9.33, they patched it so that you couldn't actually use executables anymore. So the obfuscation techniques I'm about to discuss will focus more on the actual JavaScript side of things rather than the executable side of things. So going to the obfuscation techniques, the first one, we've got the XDP file format, so XML data package. Basically, Adobe created this so they could convert PDF to an XML format. So, why is it used in malware as an obfuscation technique? So basically, it banks the principle that, as it's kind of a weird, unusual format, the antivirus vendors or their systems can't actually detect it, as they don't really know what it is. Moving on, or rather, this is actually what a XDP file looks like. So it's made up of the XML header up here. This chunk in the middle is just a base 64 encoded representation of contents of a PDF. And then there's the footer at the bottom there. So pretty basic stuff. Next up, we've got JSFUCK. I don't actually know that's just kind of it's not the technical term for it. But within JavaScript, it's possible to represent anything with these following 6 characters. So for example, this is how you represent the number 5 using JSFUCK. So I'm going to work through an example. If I do this really horribly, I apologize, but I'm just going to go with it. So this is how you represent the character E in JSFUCK. So we're going to break it down into two parts. It's got red and green. Sorry if anyone's colorblind. But, so if you have an open square bracket and a closed square bracket, that's nothing. So that's just, if you not nothing here, that becomes false. And if you not that again, that becomes true. So therefore that becomes true plus nothing equals true. So the second part here, it's, not plus nothing, 3 times, that becomes not nothing, which becomes true, which is 3 trues, becomes 1 plus 1, 1 plus 1 plus 1, which equals 3, and therefore the third item in the array becomes E. Does that make sense? Thanks, Mikey. So,
you know why they call it that, by the way?
I don't actually know.
Go look up the programming language. I'm not making this up. It's called brainfuck.
Is it brainfuck? I thought it might be based off brainfuck.
It's just like that.
Yeah.
It doesn't do anything useful.
So, the kind of principle behind it is if a lot of antivirus will kind of look for keywords and look for instances of shellcode and whatnot, and this kind of just kind of disguise it. But there is an issue. It adds complexity and adds, like, the file size will up, if you can imagine, right? So if that's how you represent E, can you imagine if you're kind of encoding an entire chunk of JavaScript with that? So execution time slows down. Next we got JavaScript string replace method, which is pretty much just search and replace. So the idea is, you take a word, so use a replace function on an object or a variable, put a regular expression, for example, what you want to replace the word with, and then the word that you want, or rather, that's what you're looking for, and then that's what you want to replace it with. So I've got a quick example up here. So var A, the dog went for a walk and the cat it passed got scared. Here in the regular expression I'm saying replace all the instances of the with the letter A, so that'll become a dog went for a walk and a cat it passed got scared. So why do we use it? So antivirus, as I said earlier, often looks for instances of like shellcode and function names. By disguising the shellcode, by basically making so it look like it's not there, and then reassembling it later on before execution, sometimes that can bypass antivirus. And now we've got this bit of a mouthful, encoding / compression stream objects using stream filters. So basically within PDFs, it's possible to compress streams, or encrypt streams, or encode them in an attempt to kind of reduce the file size. So semantic puts a while here on why is used within PDF malware. Unless antivirus software supports all compression and coding types supported by Adobe, it won't be able to decompress or decode and scan for malicious code. So this is just taking a screenshot from one of the papers that I wrote. So in terms of what you can actually compress or encode with, you get the likes of hexadecimal, base 85. We've got flate here. So flate is the default compression method for PDFs. Also images, JPEG 2, JPEG, and so on and so forth. So it's all well and good that you're compressing that data, but the PDFs need to read it. So we've got these things here called PDF stream filters. So the idea behind the filter is that once the PDF opens, it'll recognize, oh, I need to do all these things in order to read this. So this is actually an example of malware, again from that semantic paper I was discussing. So the idea is that it works backwards. So this was first encoding run length 4 times, compressive flate, and then so on and so forth that way. So this is the final output. So this is actually flate encoded. So the idea is when the PDF opens, it will read this the other way and go forwards so that it can be read in plain text and executed. So the JavaScript eval functions, basically its principle is just to concatenate strings together. Pretty kind of simple. So here we've got an example, hello world, eval A plus B would show hello world. So why is it used? It's typically used to further obfuscate other functions within, other like telltale function names within the malware. So for example, we've got here with is unescape. So unescape is used to decode, strings. And that's typically used when there's presence of shellcode. So in terms of actual methodology for this project I had to create a baseline. So I created multiple baselines, all the same. Individually added all the obfuscation techniques that I discussed there. And then at the end, I added all of them into one file. I tested them to ensure the payload executed. So I used the XP Service Pack 3 VM with Adobe Acrobat 8.1.2, which is a bitch to find, because I probably got malware downloading that as a result. And then I ran it through VirusTotal for evaluation. So creating the malware itself, I'm lazy. I use Metasploit, surprise. So the actual exploit here is the util.printf module. So the idea behind that is a buffer overflow exploit using heap spraying in versions of Adobe Reader before 8.1.3. And because I'm cliche and as a proof of concept, I just made a pop calculator. So what I did notice is the actual module applied some obfuscation by default. So this is the actual PDF stream here. And I discovered that it being encoded and compressed. So I did a bit of reverse engineering on it, which is quite fun. So first thing I did was I ran it through a PDF stream dumper, which is a good tool for basically breaking down the streams and being able to read it and reassemble a PDF. So it's great for reverse engineering. So I did that. And then I found out the object declarations and the trailer had like random hexadecimal characters placed throughout. So I replaced that back with the ASCII. And then I removed the redundant stream filters. And in addition, all the variable names are really long, complex, so I just kind of narrowed it down and made it a lot more simpler, more for myself, so I could actually understand what's going on. So before I go on, here is the original deobfuscated PDF. Header up here, here's the object declarations. In object 5, it says that object 6 contains JavaScript. This is my shellcode, and this is the physical JavaScript that will execute an open calculator. I'm not 100% sure what it does. Like this is buffer overflow stuff aren't really my forte, but kind of get the general gist of it. So first thing I did was added an XDP obfuscation. So the guy back in 2011, that's when XDP obfuscation kind of first came to light. A guy called Alexander Klink, a security researcher, published on his blog about it, and he created this Metasploit module, PDF to XDP. So basically the idea is you just give it a PDF and it'll convert it to XDP for you. So that's just like the name of the original file, the name of the new file. Pretty simple. Adding JSFUCK and as coincidentally I had to add eval as well. So I used an online tool called JSFUCK.com, but because like it was like a web-based, I could only encode like one line of JavaScript at a time. It took fucking ages. So I tried to do it in the shellcode, but I was like, this is a uni project. I don't have hours upon hours to like be doing shellcode. And encoding it, sorry. But I realized kind of in hindsight I could have probably used a smaller payload, or found another payload. But the reason why eval is required is because obviously if you're concatenating all these things together, or not concatenating, but obviously with JSFUCK you've got lots of lots of like pluses and whatnot. You're gonna have to use an eval to concatenate them all together. Next up, string replace. So where did I do it? Instances of the shellcode, instances of util.printf, as telltale sign, and also the unescape that I mentioned earlier. So I was in my room one day and I just looked around for random objects in terms of what I was going to do string replace with. So for example, goodbye, 0 guitar, 1 lamp, so that's what I'd replace it with. Similarly for the util.printf, I just did random characters, like U became A, T became X, and so on and so forth. So this is what the JSFUCK.pdf looks like. So again, similar, I've got shellcode. Oh, I forgot to actually show you JSFUCK.pdf. That's my bad. So this is JSFUCK. Just for this context, so that here, so this little bit of code here is all of this. And interesting enough, the file was big, but so the original like deobfuscated version took about maybe a second or so to execute. That took a good 6 or 7 seconds from opening the PDF before calculator popped up. So it really does slow down in execution. I think in my report, it was about, in the appendix, I think it was 40 pages worth of A4, just for this one document. So yeah, onto the replace.pdf. So here's what the shellcode looks like, or what the shellcode is. It's just all the random collections of words. Scroll down. And then here's me doing the replace. Interesting enough, on the unescape, all I did was split it up, added instances of 1 between it, and then reassembled it and replaced instances of 1 with nothing. And then save that to variable. And here we have the variable that is I think that's what actually pops the calc. So that was what util.printf became, and then I replaced it. So stream filter obfuscation, it was a bit difficult kind of to try and get it done. So I decided to just do kind of basic. So I did a base 85 in hexadecimal, and then I compressed the resulting hex into flate. So I just took the source code for the Metasploit module I did and edited it slightly. And then because I used the actual module, I had to remove the built-in obfuscation as before to only make it a fair text. So in terms of actually changing the source code, it was written in Ruby, kind of cool. Never done any Ruby stuff before. So this is kind of where the JavaScript was written. I just replaced that, everything between the line and that line there, with the hexadecimal. And then because I'd already used the hex, this function here is where it compresses it using flate. I just removed the redundant function call. So in addition, obviously the Stream filters had to change. It was pretty basic, so I just had to change it to incorporate base 85. So this one is not really much to see because it's just all kind of gobbledygook because you can't really read it in the PDF reader. But there's just a stream filter I thought I'd just show. So, as I said earlier, I applied all the obfuscation techniques at the end. So I did the string replace, then JSFUCK and eval, and then I used the stream filters and finally converted to XDP. So in terms of evaluation, as I said earlier, I used VirusTotal. For those who don't know what VirusTotal is, it's basically like an online way of, it's like an online antivirus almost. So you submit a URL or a malicious, or you think to be a malicious document, and it'll scan it for you. So there's over 60 scanning engines, but what's interesting is they're pretty hush about what capability they work at, because obviously it's a free service. You're not going to get likes of Avast or AVG giving you their full suite online for free. So take these kind of results I'm about to show you with a bit of a pinch of salt. If you want more information about that, there's a good talk at B-Sides London by Holly Williams called Offensive Anti-Analysis. I recommend checking that out. So, in terms of actual results, the deobfuscated PDF got 33 detections, which is actually alright considering I'd done nothing to that. It's straight out of the box Metasploit. XDP was really good at 15. JSFUCK and eval was 12. String replace 22. And unsurprisingly, the stream filter was 32 because I wasn't really adventurous with that. This was ran on 5th of April last year. So I know for a fact if I reran these, I would get completely different results because the engine's been updated. But most importantly, the combined file, the XDP, only got 1 detection, which I thought was kind of cool. Also, it was Trend Micro. No one uses Trend Micro, so I created a FUD. But the interesting thing that I found was that every time you run something through VirusTotal, it'll give you kind of what heuristic picked up or what flagged up. So I noticed something interesting, that multiple scanning engines detected my malware using the same signatures. So for example here, we've got Kaspersky and ZoneAlarm using the same kind of heuristic, I think, to detect it. So kind of the moral of the story is, if you can bypass one antivirus engine, there's likely chance you can bypass another one. So, yeah, that brings to the end of my talk. I'll open the floor to questions. If you don't want to catch me now, you can catch me throughout the day on the pub or on Twitter. In addition, I know a lot of presentations, there's kind of dogs. I thought I'd bring it back for the cat lovers. Yes, this is GDPR compliant. I did ask my cat if I could use this picture. And no, I did not turn the washing machine on with my cat inside it. Thank you very much. Has anybody got any questions? Sam?
Are there any more JavaScript obfuscation techniques that you maybe looked into but just didn't improve?
Yeah, there were some more complex ones. It's been like a year since I've done this, so I haven't really looked at it much, but there are other techniques to know that. There's a couple of good papers if you want me to point it in your way. Yeah. Anyone else?
Is there any particular reason why X out of 59, X out of 57, X out of...
It's more, I think it's because not all of them can read it, or not all of them are the same capability. I honestly don't know. VirusTotal, as I say, is kind of hush-hush about how they do it. But I think it was yeah, so XDP, as I said, is a bit of an unusual file format, and only 53 of the engines actually were able to run it. Anyone else?
So the heuristic that you've got up there, presumably it's a heuristic, is this PDF looks crazy, the heuristic.
Yeah, I think it is pretty much that.
And so, following off of that, did you ever try using a bunch of these obfuscation techniques to obfuscate something completely innocent and not the least bit malicious?
No, that would have been actually a good idea.
Because that would be an interesting. It's just like,
run it through.
There's a bunch of weird stuff in here. Nobody does that for legitimate reasons. Why don't we just flag this?
That would have been a good idea, actually. Didn't think of that. Anyone else? Well, thank you very much.